All right, I got OBS up and running. This is our second last lecture. Today is the second last, and then on Wednesday is our last lecture. So if you have any questions to ask, today would be a good day to ask. Wednesday would also be a good day to ask questions. You do have one homework that is currently outstanding. It is due on Wednesday. So how is that coming along? Starting it, okay. I got one person who got it done on the same day. He was on my Tuesday, Thursday class. So with that class, it was assigned on Thursday. So he spent the entire lab time doing it, and then a little bit after that. And then before I left here on that day, he turned in the solution. It's like, okay, does this work? You go like, yeah, it works, but you can change a few things, make it better. So. So anyway, do you guys have any questions about that particular homework assignment? Any concepts that I can help you clear up? No questions? All right. Well, if there are no questions about that one, the streaming is on already, so we are already streaming. And by the way, the hackathon on Saturday was kind of fun. Let me see. I don't think anyone in this. No. Okay, one person showed up. So how was it? It was good? Yeah, it was. I had to go out like on 3 separate occasions to get lunch, coffee, and then dinner. Yep, and I'm waiting for the reimbursement. But it was kind of fun. We had some students from Sac State, coming back. So they were hosting some presentations. So in addition to quote unquote the hackathon, like people just sitting down and do stuff, they were talking about Node.js and a few other things that kind of should be kind of interesting. So I'm not sure whether we'll do another one of these, or when it's going to happen. But I think it was pretty good as our first actual hackathon, and it's only really one particular student doing most of the organization. All right. So if there are no questions, I'm going to, I think last week I already mentioned what I would do in this class. It is to use, hack1.strip and kind of show you guys how you can apply what you learned in this class in terms of hacking. So I'm going to save the file first. So you can probably follow the same thing if you have a Linux computer. So right here, it's a very small file, and you can see that the file itself is only 4.6 kilobytes. It's a little executable that you can download and and run it. Okay, so I'm going to use a command line for the most part to illustrate, this kind of session. And we'll say chmod u plus x. That's the name of the file, okay? Because when you download a file in Linux, it doesn't have the permission to execute. So in order to be able to run the program, I have to change the execute permission. This won't work in Windows at all. So if you want to try this one out, it is best to use a Linux box. You can do it inside a virtual machine. So for those of you who know how to use a virtual machine, you can just spin up a virtual machine like Ubuntu or Arch Linux or Debian Linux, and then from inside the virtual machine, you can actually run this too. You would not need to have a like graphical user interface, so you can start up a very kind of plain Linux box to do this. Okay, so I'm going to run the program. Okay, when you run the program, the first thing it is waiting for is a password. Okay, so if I give you some random password, it will say RTFDMCA. Read the Fine Digital Millennium Copyright Act, or substitute whatever adjective you want that starts with an F. Okay, so the Digital Millennium Copyright Act says any attempt to circumvent copy protection mechanisms by itself is breaking the law. So it doesn't matter what you do with that knowledge, okay? In other words, if you're just curious, okay, I'm just curious, how DVDs are encrypted, and you just go figure it out, that act by itself is already illegal. Now, whether you use it to apply, whether you apply that knowledge to pirate, DVDs that you did not buy, is not the main point. Okay, the main point is they don't want people to even try to circumvent copywriting and other types of copyright mechanism. Okay, with one exception. Okay, unless you get the permission of whoever wrote that software or whoever owns the media. Okay, since I wrote this program, I hereby give myself permission to hack this program. So it's all good now. I got it recorded as well, yes. All right, so what we'll do is we're gonna run this program, okay, and we'll give it longer and longer password. In other words, I am counting on the fact, okay, or at least I'm trying to test to see if the program is poorly written so that I can use a Stack Overflow approach, at least to crash it, okay? So my first objective is to crash the program, okay? So, but using the keyboard to type, the password is not, very effective. So I'm going to write a password file, okay, as a text file. So let's just say this is password.txt, and then in here, okay, if you want to be systematic, you can always just go with a repeating pattern. There's a little bit of problem with a repeating pattern because with a repeating pattern, when we do crash the program, we'll have a hard time finding, which part of the pattern is causing the actual crash, but we'll worry about that later. Okay, so we'll go ahead and keep. So we'll keep pasting this, a whole lot of times until, I think, okay, that might be enough to crash the program. Okay, so you can also see at the lower right corner, we have 992, more than 1,000 characters now. Okay, so most people, most programmers, they go by either base 10 or base 2 numbers. If they go by base 10 numbers, 1,000 would be a fairly reasonable number that people use as a buffer size. If they use base 2, then 1,024 would be a fairly reasonable number that we can kind of count on. So I don't know whether this is going to crash the program. Okay, so I'm going to save the file first, and then I'm going to rerun the program. Okay, when I rerun the program, I'll redirect the input from the file that I just created, and this time it did crash. Okay, which is a good sign, because if a program does crash, that means it is not it is not, how should I put it? It's not checking the size of the input. Okay, the size of the input being too big is causing the program to crash, which means the programmer might have forgotten a few other things too. Okay, so this is good. Now, when you're running this kind of attempt, there are other ways to feed input into a GUI program. Okay, so there are many other mechanisms. Instead of just using the command line tool, there are other ways to kind of attempt to crash a program. Okay. So now that the program does crash, it only gives me a segmentation fault, which is not very helpful because all it says is the program eventually goes to a place that it's not supposed to, or it's trying to read from a location that it is not supposed to. So that's not very helpful. So what we'll do is we're going to enlist the help of our friend GDB, okay, which is a debugger. So when we run hack1.stripped from inside the debugger, we can just run it, but this time also use the redirection. So we are still using the same password.txt file as the input. Now the program crashes again. And the stuff in dark blue is difficult to read, but it says, a bunch of zeros here, and then it ends with 40059B. Okay, and that's all it did. So the first few things we want to do is to do an IR or info register. So this is showing us, all of the registers. This is in 64-bit mode, okay? So you can see how we have RAX, that's kind of register A, and then we have register B, C, and D. RSI, RDI are other registers. RBP is our frame pointer, which we don't have in this class, okay? Because we only got 4 registers, and we cannot afford to have a frame register, which is very handy when you need to access local variables and whatnot, but we don't have it. And then the next one is something that we do have. It's RSP, it's the stack pointer. So you can also see how the stack pointer is pointing at this particular location, which is kind of low, okay? Because compared to the frame pointer, they're off by a whole lot, okay? The frame pointer somehow is not, it's kind of way off. And then we have a bunch of other registers, and then we have the flags register, which we're not concerned about in this case. Are we still doing okay so far at this point? Okay, so what we want to know now is what exactly is on the stack, okay? And what instruction is at the location when it crashed. Okay, so there are several ways to do it. Okay, let me continue. So we'll see. We'll just press enter. This register is also important. It's called RIP, which stands for instruction pointer. Instruction pointer is our program counter. It's just named slightly differently, but it serves the same purpose. In other words, the instruction that is offending, that is attempting to access a location that is not supposed to, is at this location, 40059B. So does it make sense that we want to go there and at least know what instruction it is? Okay, so we'll go ahead and do it. The command to do it is called X, which stands for examine. But of course, I cannot remember how to use examine because I only do this once per semester. So here's the X command. It says X slash, and then you can use one of these letters to represent what you want to do. We want to disassemble, which means we want to display the instruction at a certain location. So it's going to be X slash I. And then the location where we need to go to is whatever our IP has, okay? And using a $sign, I can refer to the register inside the debugger. So that this way I don't have to copy and paste stuff. And it says it's a return instruction, okay? RETQ is a quad return instruction. The quad has to do with how many bytes it's expecting from the stack, when it's trying to do the return. So we're crashing when it's returning. But what can possibly cause it to crash when it's trying to return? It must be trying to return to the wrong place, okay? So let's go ahead and check out what is on the stack right now. In other words, what is it attempting to use as the return address, okay? Does that kind of make sense at this point, okay? So the return address is 64-bit wide because this is a 64-bit architecture. And 64-bit using the X command is we have to use G for giant, which is 8-byte long, okay? So we have to do X slash G, and then we also want it to be displayed in hexadecimal, which is another X here. And we want to see what is at the stack pointer, so it's RSP. And this is what it is attempting to use as a return address. Because at the return instruction, it is supposed to use whatever the stack pointer is pointing to as the return address. It's really just like the same way that we do things in this class, okay? So when you look at this sequence here, apparently it is just kind of random stuff. It doesn't seem to make any sense, but it does, okay? So do you see how 3839 are in a sequence? And then we have 61, 62, 63, 64, 65, 66. Those are also in a sequence. So this turns out, if you look up the ASCII code, 38 is the ASCII code of 8, the digit 8. 39 is the ASCII code of the digit 9. 61 is the ASCII code of lowercase a. And then 66 is the ASCII code of lowercase f. So we have 8, 9, A, B, C, D, E, F. That's the kind of stuff that we put into our password file. Is that okay? Now, we don't know exactly which sequence because we have a lot of sequences, right? So we have to do something about that. But we do find that, hey, somehow, the password is ended up on the stack as the return address. So when the program is attempting to use the string, 8, 9, A, B, C, D, E, F, as a return address, obviously that's not going to work. And that is what's causing the program to crash. But this is very encouraging, okay? Because as a hacker, what I'm trying to look for is situations that the programmer should have anticipated, like, oh, your password is way too long, I'm not even going to process it, okay? But instead, whoever wrote this code, myself, you know, just says, we'll just copy the entire thing, into a buffer, and then we'll do some comparison, okay? Without checking the length first, okay? All right, so this is all good, but we cannot proceed any further unless we change our password so that we can see which sequence is getting affected, because they all look the same, right? This is our password file. So what we'll do is we're going to change the 8, because that's the, was it the 8? Yep. So because the 8 is the first letter that is causing that can be identified. So I'm going to change these so that we have uppercase A, uppercase B. Okay, I'm not going to look C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, oops, that's T, U, V, oop, uh-oh, my keyboard just got locked up. UVW. Oops. X, Y, Z. Okay, so I'm not really sure whether I have gotten to the point where it will still crash within one of these 26 sequences. Okay, but so we'll give it a try. So we're going to use the new password file. It crashes again, which is fine. And then we'll do the x/q giant, which is G, X, and then whatever the stack pointer is pointing to. There we go. And yep, we got it. Because this time, it is crashing, and instead of the 8, it is a 5.2. So we have gotten to the point where it's one of the sequences that we have already modified. So what we need to do now is to find out, okay, exactly where is this 5.2. Okay, so we'll go ahead and test that. Okay, and we have to look at the ASCII table to find out what is the letter corresponding to 5.2. So 5.2 is corresponding to R. Okay, so the sequence that starts with R and then 9 and then A, B, C, D, E, F, those 8 bytes were used as a return address. Okay, so we go to password, and then we locate uppercase R, okay? And we want to keep all of this stuff here, but everything else, we can just kind of toss away, because, that's these bytes here, okay? From this R all the way to F, these are the bytes that were used to serve as a return address. So I don't need the rest of the program, because now I can reliably reproduce the result of this particular problem. Are we still doing okay so far with this? Okay. Now, I'm not going to ask you questions like this in the final exam, okay? Because this is for a completely different architecture. However, based on what you have learned in this class, how we use the stack for returning and stuff like that, yeah, I think it's not unreasonable that most of you should be able to understand at least the general idea of how this is happening. Okay, so this is all good, but now the question is, now since I have control over the file password.txt, I actually have control over where the subroutine is going to return to. By modifying those 8 bytes, okay, in the password file, I can now say, instead of going back to where you're supposed to go back to, now I can tell you where to go to, okay, which is great, because I want to bypass the password asking and checking part of the program, Okay, I want to go straight to the program where everything is unlocked, all the features are available. Okay, so the next thing I need to do is to disassemble the program to look at the source code. So this is not unlike one of your questions in exam 2 where you were given the assembly language code and then you have to kind of decode it and find out what it does. Okay. But before we do that, I want to run the program one more time, give it some erroneous password, and want to kind of focus on the message. Because this message here this is the clue, okay, of whatever is printing this code or whatever is printing this message is close to the conditional statement of some kind that checks the password, okay? Or at least that's what I'm hoping. Are we good so far? So we want to look at this particular thing. It should be somewhere in the executable. That's the whole idea. Okay. So I have a program called hex dump. Hex dump. Okay. -c means I want to list everything by characters, and then we give it the name of the file, and then we pipe it through less, because less is more. Less is more than more, I should say. How many people know what I'm talking about? Okay, very good. Less being the program has more features than more the program. It's basically just a pager, but you can search for stuff, okay? So I'm gonna search for RTF, okay? Hopefully, oh, okay, we found it, okay? So basically every string, unless you have a specialized program that can kind of, try to obfuscate stuff, so that literal strings do not appear as they should, most of the time you can find the literal strings somewhere in the executable. So now we can see that, oh, okay, we can see that we are at location 67 at offset, sorry, we're at offset 670, and that's where the message is, okay? So I'm gonna pull a Post-it and remember that. Okay, so let me see, can I make a new Post-it? Nope. Nope, okay, well that's fine. I'm just gonna use this Post-it here, get rid of everything that's already there, and then we'll just write down 670 as the offset. And this is in hexadecimal, okay, because this will come in handy later on. So now that I have a clue of where the message is, now I want to see, where, do I make use of this particular string? Because this string is passed to something that prints, in the output. So I need to find out where the call is. Okay, so I get out of this. Now I have another program that I can use. It's called object dump this time. Now, I cannot remember how to use object dump, but that's okay. That's what man pages are for. So I want to use object dump, and I want to disassemble the entire executable. Okay, so I can use /D to disassemble the entire program, because the objective is find out where am I calling a subroutine and print the message that I just located. Because I know the location of the message now, I just need to know the call of which subroutine is making use of that message. So I'm tracing my way backwards based on what the program displayed on the screen. I'm now going backwards to find out where is the logic that determines whether I enter the right password or not. So -D, so we have hex dump or object dump, -D, same program, and we'll feed it through less just so that we can examine the content. Okay, so we are looking for 670. Okay, so we search for 670. Okay, here's a 670, and it is the right place already. Okay, so in this case, instead of using LD or ST, there's an instruction called the mnemonics called MOV move. Okay, which is a very bad choice for the mnemonic because you cannot actually move data. Moving means once the data is moved from the from location, is no longer at the from location, right? I can give you a quick demonstration. Here's a marker. It is now here, and after I move it, it is no longer at the original place. But you cannot move data. You cannot move bit patterns in a computer. Okay, you can only make copies. Okay, so move is really a bad name for a mnemonic. It really means copy. In this case, I think it copies from, let me see, from which direction. It moves to the right hand side. Okay, so this is opposite to the direction of our assembly language. So it's moving this constant blah 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 670 into register EDI. And in this particular, in GCC, if you only got one argument to pass, it can be passed using just registers. Okay, so that's a different convention because they have a lot more registers than we can play with. Yes, go ahead.
Movies like LDI.
Hmm?
Movies like LDI.
It's kind of like LDI, exactly. So it's like LDI, except the direction is reversed. So in our programming, in our assembly language, it would be equivalent to LDI, D, comma, and then whatever that constant is. Yep.
Since this is a non-RISC architecture, do all non-RISC architectures have pop and push?
Yes, most of them have push and pops.
Okay.
So instead of doing what we have to do, like with a few instructions, you just say pop or push.
Is that less efficient?
Okay, so when you ask, is it less efficient? You have to kind of be more specific, because efficiency comes in different forms. Okay, because efficiency is usually measured as some quantity divided by some other quantity. So if you're asking, how much can we do per line of assembly language, or per line of instruction, then yes, absolutely. Okay, a cisp is far more efficient when it comes to how much work can be specified per instruction. Are we good? Now, if you are thinking about, what about how much stuff can be done per second or per clock of the processor? Well, a cisp processor may win that too. Okay, you can actually get more things done per clock, which is good. Okay, but remember what we said. Did I mention about the data center? What is limiting how much processing can be packed into a data center? Heat. So in terms of heat or heat dissipation, a cisp processor is not as efficient. So the amount of processing that can be done per unit of energy is actually not as good as a RISC type processor. That is where a cisp processor is going to lose. Is, okay, if heat dissipation is an issue, it is no longer as efficient as a RISC processor.
And why would it produce more heat for push or pop when it's the same?
Because there are more transistors inside the processor.
Okay, to abstract that, you would have to have more transistors?
Right. Because remember, everything is done in hardware, so the complexity of this cisp processor is going to be more than the equivalent RISC processor, which is also 64-bit wide and be able to do all this processing.
But we made a ROM slice for on our test. Can you just make a ROM slice for push and call it?
We could do it to a certain extent, yes. So we could implement a push and a pop. In fact, the instructions that we did, that I did ask in the exam, is actually, a much more general version of pushing or popping, depending on whether you're talking about this class or the other class. Are we good so far with this? More or less? Okay. So we know that this is, the branch that says, oh, sorry, your password did not match, okay? So maybe around here would be the code that says, yes, you got the right code. So we're gonna poke around a little bit here, okay? And see if we can find, something that might be useful. Now here's another return instruction right here, okay? So whenever you see a return instruction, that means whatever is after it is most likely the beginning of another subroutine, okay? So this is most likely the beginning of another subroutine. And then we also have test, okay? So test EAX is kind of the same thing as our AND AA, okay? It's really just checking whether A, against, certain flags. And right here, we have a JE instruction. JE is the same thing as our JZI instruction. In other words, if the Z flag is set, this is where we're going to call. That means if not, this is where we're going to call. Are we good so far? Okay. So you look at this thing here, okay? Do we kind of recognize this address, 4005BA? Can anyone see 4005BA somewhere else on this screen? It's right here, okay? It is matching the code that eventually will print RTF DMCA and an exclamation point. Is that okay? So if JZI, okay, what we know as JZI, but it's called JE for jump if equal to. If J is going there, what do you think the other branch might be doing?
Go to the right answer. Compare it to the right.
Where I want to go, right? Okay. So in order to double check that, we might want to check what is at location 654, because we know at 670 we have that string. Okay, we have the RTF DMCA exclamation string. So we might want to check what 654 is corresponding to, because that is also being called using putS, which is a way to print something onto a standard output. Okay, but before we go any further, it might be a good idea to write down the location that I want to go to, which is this location here. So we're going to write down 0x4005AE. Okay, and we'll say this is the branch that we want to end up at. Okay, yep.
This is a question of the dump file.
Uh-huh.
How do you protect against dumping someone's file?
You cannot.
Because it's
For
straight from the
any program that is installed, okay, on a client on a computer, is dumpable. Okay. Now you might say, okay, but can we make Windows, so that you other than executing a program, you cannot copy a file, you cannot examine a file, you cannot read a file? The answer is maybe. Okay. If you have control over the operating system itself, you may be able to restrict how a file can be accessed. Okay.
That's only on your end, right?
That's only on your end.
So if you downloaded someone else's, say, program and you wanted to see how it was compiled and ran, you could go through this and
Yes.
find out.
Yep. And the same approach can also work in Windows. Okay. I just chose to use Linux because the tools that I'm familiar with, they all run in Linux. But in Windows, there's a program called Debug, DEBUG, that does almost the same thing as GDB. Yep.
I don't want to get off track here, but we're doing move 0 into EAX on 4005A0.
At which instruction?
4005A0.
5A0.
Close to the top.
You mean here?
Yeah, we're moving 0 into EAX.
Uh-huh.
But is that the same EAX that we're testing online, like 4005AA?
So this one is moving a 0 into EAX, and then it's calling this particular subroutine.
Does EAX going to change after calling the subroutine?
Possibly. We don't know yet whether it's going to change or not. But EAX is used as the return value. That much we know. Because that's a compiler thing, and we know that the compiler would use EAX as a return value after the function is returned. So whatever this function does, okay, when it does return, EAX contains the return value. And we are using the return value from that function call to decide whether we think we have a match or we don't have a match. Okay? All right. So what we're going to do now is two things. Okay, we want to confirm this string here is corresponding to a message that says it is all good. Okay, so we'll write down here, check location 654 for a good message. Okay, so we got a few things going here. Okay, so now we can get out of displaying the dump of the program. So this also brings to another question. Okay, so if you wrote a program, okay, and you really don't want people to copy it or figure out how it works, what would be the best way to do it? Answers, suggestions.
Obfuscate the source code.
You can do that, but you can only do it so much, right? Because people can unscramble your code too. So the best way to do it is to run it as a service on a server, somewhere else. So it's a remote procedure call, basically you send a package to the remote server and say, okay, these are the parameters, this is what I want to do, and give me the answer back. So the execution is actually on an entirely different machine over the internet. So whoever is trying to crack the code would hopefully not have access to the executable itself. So to run basically a library as a remote service is one way so that people cannot crack your program. Okay. Yep.
You can do it piece by piece. Say if you try dumping the file from each bits that came to you, based off.
No, because you're only getting back the results.
Oh, okay.
You're only getting back the results of a normal function call, so you cannot really tell how the other your computer is doing the processing to give you the answer back.
So you have to crack, or you have to somehow break into the server to figure out.
Right. So now you have one more barrier. Okay, so there, and also with that one you have IP addresses that can be traced. So there are a lot more fingerprints that will be left behind. Whereas doing it this way, it's completely localized. I can turn off my Wi-Fi right now, and it'll still work. Yep.
This is a tad bit off topic, but I was reading an ebook on Kindle,
Uh-huh.
and I wanted to copy and paste the text to cite it for my English project. So
Uh-huh.
they wouldn't let you do that, and I was using it online, so I was like, okay, I'll just look at the HTML code. But in the HTML code, they made they put every word into a div and a class. So you can't really.
It's
get to
huge,
the
right?
words. Yeah, that's how they obfuscated it. I couldn't copy and paste it because I'm copying and pasting like 1,000 div tags.
Well, but the div tag is easy to disassemble.
And classes, yeah.
Yeah, because if you have the HTML document, there are libraries in Node.js that can basically just say, okay, strip all of these divs and whatnot. I mean, that's pretty easy to do once you know how. Once you have the HTML file, it's pretty easy to do.
Yeah, I was thinking about doing that with Python, but it's like I'll just.
Yeah, Python has the correct libraries too.
I'll
Yeah.
just read it and code it would be a lot easier. But
Yep.
it was interesting where they obfuscated it.
Yeah, I'm not sure whether it was the intention. The intention was to obfuscate or not, because in that case, it's a pretty easy thing to strip all the div enclosures. So I think they might have some other reason why it is there. It sounds like it's just very inefficient coding from my perspective.
Do you just protect them from the average Joe from copy and pasting the whole book?
I don't know. I mean, and HTML is very easily parsed. I mean, there are tons of libraries that can parse it. So by the time it's already in HTML, the content is it's not safe. Yep. All right. So we're going to check out these two things. I'm going to exit out of object dump. All right. So the first thing is to go back to hex dump, and then we want to go to offset 654. So 654 is not easy to get to because it's not ending with a 0. So we want to kind of scan it. 654. Okay, we can find the message here. Welcome back, comma, trusted user. Aha. Okay, so we have a confirmation that 654 is in fact the location of a string that confirms that we got the right password. So with that confirmation, we'll also know that this is where we want to get back to. In other words, we want to modify the password file so that by overflowing the stack, we overflow the stack specifically so that we can get back to that location, the location where I will continue to execute a program and everything is good. Is that okay? So this is what we want to do. But we have a little bit of a problem because what you can type into a normal password file, they can only be things that are printable characters, okay? Because you cannot, these ASCII code, AE does not correspond to a character, okay? It is because characters can only go up to 7F in the ASCII table. And then 05 is also not a printable character. 40 is okay. I mean, it is actually a printable character. And then we also have implicitly a whole bunch of zeros on the left-hand side, because remember, this is supposed to be an 8-byte thing, and these are only specifying the least significant 3 bytes. So we do have a little bit of an issue here of how do we modify the password file so that we can actually specify this particular return address. Okay, so we're going to do some work with that. Okay, let's see. Yep, I have hex edit, which is hexadecimal editor. So this is a really cool program, for hackers, because you can go into any file, okay, whether it's a text file or whatnot, doesn't really matter, and it gives you this, kind of hexadecimal editor. So what we need to do is to go to the location starting with the R. The R is this 52. The R is the least significant byte. So what we need to do is to specify the sequence that we want in a backward manner. In other words, AE being the least significant byte of the address needs to go here, needs to go to 52, because the Intel processor is known as a little endian processor, which means if you have an integer that takes up more than 1 byte, the least significant byte has the lowest address. So AE is going to have the lowest address, so it belongs here. And then the 05 goes to the next location, and then the 40 goes to the third byte. And then the rest can all be zeros. Are we good so far? Okay. So that's what we're going to do. So we specify AE as the least significant byte, 05 as the second least significant byte, and then the 40 as the third byte. And then we have to kind of zero out the rest of this file. Okay. So we want to save the file. I think it's Control X and then confirm. So now the file is saved, and we'll go ahead and run the program again. Now, if you want to be sure, and if it does crash, you want to catch it, you can run it in GDB. Yep. Open it in what? In Vim? Oh, okay, sure. Yeah, Vim will go like this. Vim says, I have no idea what some of those bytes are. The control at is are the zeros, so it knows the. Okay, so let's go to the end here. This is our AE. This is our 04, and this is our 40, and then we have 6 zeros after that. So it's sort of display it, but I cannot enter anything this way, not easily. So it's a lot easier to use a hex editor, because it just knows how to handle. It just looks at a byte as a byte. It doesn't interpret. Is it printable? Is it line feed? That sort of thing. All right, so we're gonna run GDB this time, with hack, just in case it crashes again. I can catch it and kind of refine how I hack this program, but I am fairly sure that it's gonna work this time. And you can see how it says, welcome back, trusted user. So I just, hacked my own program, by manipulating the password file. So what's happening is I have a local array in the subroutine, and the subroutine, that's responsible to process the password file, just did a function call to read all the characters in without checking how many bytes are being read. So it's going to fill up the internal buffer, the local variable buffer, but because I did not check the length, it will also potentially overflow past the array. So it can overwrite the return address in this case. And that's how I can get the program to do something erroneously, to basically say, okay, this is how things are. Okay. Now, there are other issues, with this approach, because, when I return from that subroutine, it is not supposed to return to the main program directly, okay? So it might have skipped a few invocations. So EBP, which is the frame pointer, or RBP, the frame pointer may actually be off. It may not be what it needs to be, but I can collect other evidences, to find what RBP should be, or I can just kind of sequentially test locations until I find the right location, so that the program will actually perform and function the way it's supposed to, even though I skipped skipped a few frames when I just jumped directly to one point. So are we okay so far with this approach? I mean, does everybody kind of have an idea of how the program was hacked and how we utilize what we learned in this class, which is really just, oh, we have, the return address on the stack, how we, evaluate assembly language code and decode the conditional statement. Okay, if this part is the branch that says, we're not supposed to have access to the program, maybe the other part is saying that we do have, access to the program. So we're basically using some of those skills, in this class to kind of crack the program. Are we okay so far? Sorry, go ahead. So does it? Yeah, go ahead.
This is just hypothetical, but if the program had a hard-coded password in it, could you run strings on it and pull the password out of this assembled source code?
Yep. Well, the worst part is if the program does not have a hard-coded password and instead is reading it from a file, because we gain control, right? So if we might be able to search through the memory space and find out which file supply the password. And now let's just say that, okay, but maybe the password file itself is not MD5 but SHA-2 encrypted or is hashed. Okay, we might be able to locate the key for the hashing as well. So that means you can go back and crack a lot of things, and you can also directly inject the SHA code after the hash function. So you can do a lot of stuff, even if the checking of the password is not simple like this. The key is once the program crashes, you can now move in and because now you have control. So the idea, if you want to write code, that cannot be cracked easily, don't make it crashable. Now, if a program is not crashable, I can still disassemble it. Okay, but just because I can disassemble it doesn't mean that I will have a way to kind of look into and be able to exploit it. Are we okay so far with all of this stuff? Maybe. Now, this is just a program, okay? The program is running in user space, which means, yeah, I might be able to crack the program, but the worst I can do is to access a program, where it is not supposed to give me access to, okay? But in terms of, trashing the operating system, installing a rootkit, that sort of thing, probably cannot do anything close to that because this program is running with a regular user permission, so it cannot really do any system-wide damage, okay? What can cause a system-wide damage? Yes, but what kind of program runs as root? In other words, I'm trying to find what program I can crack in order to really get a lot of access into the operating system. So how would you approach that? So what we do something like this, okay? We look at all the processes, and then we ask what processes are owned by root. Okay, so you can see that there are a lot of processes owned by root, but many of these processes are not, under your control. So what you want to look for would be something that interacts with the network port, something that listens to a network port, because those are the ones that you can remotely hack into, like the TCP IP stack, okay, and stuff like that. Okay, but when you try to crack a program or when you try to crack something remotely, then you basically do the same thing. Has anyone heard of a Windows exploit? This is from like a really long time ago, so I can show you that. GDI plus exploit, and it's a long time ago. Okay, and it should show the date. Okay, it's because of a buffer overflow. Some of these exploits, they utilize certain fields inside a bitmap, inside the image file. So if you look into a JPEG or a GIF file or PNG, there's a certain part of the file where you can say, okay, you are allowed to have up to this many bytes for comments, okay, for the geolocation and blah, blah, blah. But it typically is not just null terminated. Typically, there's a maximum limit of how many characters you can put into that portion. So one of the exploit is to say, okay, what if I have a null terminated string that is much longer than the maximum size of where that space is supposed to be? And that turned out to be successful. So someone can upload a cracked or a manipulated image onto eBay. Okay, so this is a iPad. Okay, a picture of an iPad, but it has that exploit built into it. So just by going to YouTube without you doing anything, just by viewing the image of that particular iPad, can cause your Windows to be hacked. Isn't that wonderful? And because the crack is at a Windows level, so your protection, okay, you running as an end user, may not be able to protect that particular exploit from actually changing your operating system because it is at a core level of the operating system. Is anyone interested? Doesn't look like anyone is. Terrifying. Okay. So there are other exploits too. Okay, I can point out a few that are really interesting, and these are mostly software stuff. One is called a Heartbleed bug. Okay, you can actually somebody wrote a website just to explain what the Heartbleed bug was. Okay, and this one was it's actually on a open source code. So open source is not any safer sometimes, okay, except when it does get identified, it gets fixed pretty quickly. So for those of you who want to know exploits, this is one interesting exploit to look into too. The whole reason why it's called a Heartbleed bug is because it is exploiting the heartbeat feature of SSL. With SSL, running on a server, the protocol supports a particular kind of packet, where you can send a packet to an SSL, enabled server and say, "Are you there?" Okay, it's just like a ping. Okay, and then the server will go like, "Yep, I'm still here." Okay, and should not be disclosing anything that is particularly important. But somebody found a way to exploit the packet and request something back. So the server will now come back with the content of some random location on the server itself. Okay, most of the time it would just return some garbage that you would not be able to use it for, but occasionally it will come back with the encryption key of the SSL server itself. And other things that are actually important. Yep.
Wasn't there an Intel problem? Like Intel, and Intel, I think recently there was a problem with Intel where they had a protection issue. I think
Is it a hardware issue or a software issue?
They had to recode their processors.
Yeah, I cannot remember. Is it called Spectre?
I think so.
Yeah, Spectre is one, and then there's another one. There were two hardware exploits. One is Spectre, and the other one is something else. Spectre.
Meltdown.
Huh?
Meltdown.
Meltdown. Okay, thank you. Meltdown. Now these are very interesting too because they relate to the actual architecture in terms of how the gates and how the hardware components are arranged. So when you look up these two, they are hardware-based hacks. In other words, one of them, would actually be it would work on both Linux and Windows, and then the other one only works on Windows. I cannot remember which one is which one, but both of these were based on a race condition, and I think it has to do with caching. And it's interesting. It's because it's a hardware level exploit. It's not even software. The software person can be going like, okay, I'm doing everything I can possibly do to secure the program, and can still happen. What ended up, what operating systems ended up doing was they had to turn off, some kind of caching mechanism, making programs go a lot slower, but that would also fix the potential problem.
That's what I heard, that their processors ended up being a little bit slower.
Not a little bit. I think it was. I think it was. It was significant. Yeah, it was. It was significant, and it also, if I remember correctly, this is one of these two also crosses architecture too. So it's not just Intel. Both Intel and AMD got affected by one of these two. The other one is only Intel. Yeah, it is. It's interesting. It's interesting not only because exploits happen. Okay, ever since the first day people write programs. Okay, thanks to von Neumann, right? He's the guy who says, hey, instead of hardwiring everything with wires and actually change the program by opening up a computer, he's the guy who says, let's store instructions in memory. Okay, ever since that day, okay, exploits and software bugs started to exist. Okay, but nothing is like, how should I put it? The impact, okay, of those bugs and exploits, they change over time. So we don't have to go back too far. Okay, let's just go back to the early 90s. Let's say 1990. Okay, how many people have a computer that's capable of going online? I mean, there are some people, but not a whole lot, right? And how fast was the internet? It wasn't very impressive, okay? It wasn't very impressive. Some people have computer access, and if a household had a computer back in 1990, it's like, wow, okay, that's pretty cool. Now we have how many devices?
12 is in my house is 4 people.
Okay, not just right here, okay? I have 1, 2, 3, okay? And then 4, okay? So I have 4 devices running some kind of software that is internet connected, either directly or indirectly, okay? When you go home, okay, you look at your dishwasher, you look at your laundry machines, and you might say, those are too expensive, go ahead.
Those are connected to the internet.
Those are connected to the internet. Now I have this one I have to show you, okay? Since we're on this track, gotta show you this one. It is a microwave oven. Now you might say, your attack, you must be talking about something that is way out of my budget, okay? Maybe it is a $2,000, microwave oven that is internet, connected. Big deal. I'm not gonna buy that. I won't have money to buy that. No, this one has a Alexa, built into it, and it's an Amazon Basic microwave oven. So we'll check out how expensive it is. Is it out of my range?
Yeah, it is sold out.
Sold out. Fine. Before it was sold out, it was $50. It was $50. If it were $5,000, it wouldn't sold out, right? It would just still be here. It was $50. So for $50, you can buy a 700 watt, which is not the best, okay, but it works. You can buy a microwave oven for $50 that has Alexa built in. And Alexa requires internet access, okay? You cannot have Alexa without, internet access. And I very much doubt that it relies on the Cat5 cable. Who's gonna route a Cat5 cable from the microwave to the main router in order to make it work?
I want gigabyte faster internet.
Exactly. So, I mean, that is the kind of stuff that we are dealing with here, okay? The Internet of Things, everything is now internet connected. The locks of a lot of houses are now internet connected too. The boat, is now internet connected, okay? Along with, security cameras and whatnot.
The doorbells too. The screwdriver, and I've pressed somebody's doorbell and it activated their intercom. They started talking to me from wherever the heck they were because I was at the wrong house.
Yep, I have Ring. You mean I have Ring on my doorbell, quote unquote, as my doorbell. So someone can be pushing the bell button, and I can answer from here, right in the middle of a class, and say you can just leave the package, in the porch. And there's no way that person can tell whether I'm in the house or I'm halfway around the world. That is the sort of thing we're dealing with, okay? So if you assume every piece of software has some kind of flaw, okay, may or may not be security related. Maybe it just crashes, okay? But maybe it's security related. Can you kind of imagine, what kind of inconvenience and what kind of problems we can run into, when these devices all get massively hacked? The power grid is getting that way too. The power grid itself is being, computerized or being automated. Okay, how they route power, from one substation to another substation, all kinds of stuff is now computer, controlled.
PG&E apparently.
PG&E,
Well, at least their old hardware in like California.
well, most of California already has a smart grid, system, which means a hacker can potentially remotely shut down the power grid, or at least cause enough inconvenience, that most people will start to not be happy. Yeah.
Who would have time to hack a CPU, like the Intel, exploit the Intel problem? Like you'd have to understand the architecture, wouldn't you?
I can think of like at least two fairly populous countries who are not, one particularly is not on friendly terms with the United States, which I would not name. Okay, and they got a lot of people, right? I mean, so looking for exploits, you can either have a bunch of a small number of very smart people, or you can have a lot of just kind of smart people. Okay, because it really boils down to how many people can put in their energy and time into looking into stuff. Now you might think your Alexa microwave is not a big deal. Okay, hack my microwave and burn my food, big deal, right? But that is not the case, because they can use the microwave. Let's say they hack into the microwave, okay, but it's already sitting inside your Wi-Fi network. Okay, most computers would consider LAN a little bit more secure, and they do not put up as much defense against something that is from your LAN instead of from outside, which is WAN. Wide area network versus local area network, right? So when you set up Windows, okay, I'm pretty sure most of you have done this already. When you go to somebody's house, you say, okay, this is the new Wi-Fi connection, da 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 da, and Windows will ask you, okay, how much can I trust this network, right? And most of your computers inside the same household would just say, well, anything within this subnet, we can trust. Well, but guess what? Your Alexa just got hacked. And now it is trusted within your LAN, within your local area network. So now it can be the staging area to launch attacks against your other devices. The first device that probably will get hacked is your router. Because if you get to the router first, that means now everything is wide open. Because the router is what is stopping an active connection from being made to things that are inside your household. Because anything that's incoming, all the incoming requests, most router by default will just drop them. So nothing can actually come in. So so once your Alexa get hacked, it will find out what router you're running, and it will find out whether your router is patched correctly. If it is not, then the router itself would be the first one to get compromised. And then once your router is not protecting, then the rest of the machine in the network would also be somewhat open to attack from the outside. And now you have to think about, well, I'm pretty sure the microwave is secure. What about your speakers? What about your Alexa speakers that you have distributed all over the house? Yeah.
Now I'm gonna get a Raspberry Pi and do it through a server.
Sorry?
Now I'm gonna buy a Raspberry Pi and do everything through.
You can get Linux to run on some of the routers. So there are special distributions of Linux that are specially designed to run on routers. So you can kind of do that. But we are talking about massive scale here, right? Car is probably internet connected, somehow.
I think Teslas are.
All Teslas are internet connected, which is good and bad at the same time, because who would steal a Tesla? Someone who wants to be caught. Because a Tesla can be remotely disabled, and it knows its current location too. So even though you may not be able to lock all the doors and lock the person inside the vehicle, you will still be able to tell where the car is and then send the authority to that location. So stealing a Tesla is like why would you do that?
I'm suddenly happy now that my car is 30 years old.
A Tesla is kind of like an iPad but with four wheels and a motor,
A bit more valuable.
or maybe two motors. And with the Cybertruck, three motors. Yeah, the Cybertruck can outrun any Porsche. So are we okay so far? Okay, is everybody convinced that computer security is increasingly important, for the foreseeable future? Yep.
Well, so how worried are you about like Bluetooth and other stuff? I mean, because it's a way shorter range.
Right. So Bluetooth, has a quote unquote shorter range. Okay. But you have to take into consideration that some people can do Wi-Fi or Bluetooth sniping.
Okay.
Do you guys know how many people know of that term? Bluetooth or Wi-Fi sniping. Okay, so you can custom build. Okay, you don't have to buy the antenna. You can custom build an antenna that is very directional and has a high gain. So that way, even though a regular Bluetooth device, only has like 30 feet of range, you can greatly extend that, by using a directional antenna in conjunction with a signal amplifier.
Okay, so you increase the range of your. Okay.
Yep. It doesn't work as well in Sacramento, but if you're in LA, like downtown LA, where there are a lot of high rises, if you gain access to one of the rooftops, you can snipe a lot of offices and break into people's phones and printers and whatnot.
So do you wrap your house in tinfoil?
A jammer, right?
I mean, how can I connect my iPad to my earbuds to my?
Yeah.
But is that something that you think maybe people will look into in the future? Some sort of building material that would prevent certain frequencies from passing through the walls? I mean,
You can do well. Tinfoil doesn't work as well as what we call a Faraday's cage.
right, yeah. So are all houses going to be?
I mean, you have RFID blocking wallets,
Right.
right? I mean, so it's not like people have not thought about that. Yep.
Isn't that kind of a conflict of interest though? Because people still want to be connected to the internet, so you have to have some way to
But not from. But the way you're connecting is to your own router that is inside the building, right? You don't want anyone from outside the building to be able to eavesdrop your network, traffic.
Yeah, you hardwire in.
Would that disrupt the signal from your phone too?
But the problem is 5G is going to be, a lot of the 4G, 5G, frequencies are kind of close to the 2.4 gigahertz of Wi-Fi and also Bluetooth. So that get impacted as well.
Could slow down your phone. You'd be instantly have 3G internet speeds.
Yeah, so you cannot have the cake and eat it. So that's the problem. You cannot have the cake and eat it. So there I think there will be some very interesting stuff happening.
Using lead paint again. Yeah. Paint the windows.
So so for anyone who's interested, and see the value in computer security, I think there are a lot of opportunities. Four-year universities are kind of behind the curve right now in terms of offering computer security related classes. So you pretty much have to kind of learn this on your own, read extra books, take extra classes. Okay, we have some CISS classes here, computer security classes over here. They don't teach you very advanced topics, but at least you get a general idea of what is involved in computer security. This is also something that I learned this morning. China has specifically said that it has informed all of its government agencies not to purchase any computers or computer-related equipment from the United States. Not sure whether it's computer security related or trade war related, or both. Okay, but they are gonna it's on their radar.
I mean, did the same thing with Huawei, didn't we? Just say cut them completely out.
Yep.
It's just trade war thing. Well, yeah, but I mean, it's the country's starting to because it can be compromised.
Well, but that $50 Alexa-enabled microwave is very likely to be made in China.
Yeah.
Yep. Which means if they change the firmware, you have to double check everything, because if they change the firmware to include backdoors and whatnot, how would you know?
Do you think it's kind of fruitless to get into like computer security if quantum computing will bypass all of that in a short period of time, potentially in our lifetimes? You know?
Yeah, but quantum computing is still a long way from reality, as far as we know. I was watching some documentaries on quantum physics, so they can do certain things right now, but to build an actual full computer, we are still not quite there yet.
Well, you mentioned earlier in the semester that even in our lifetimes we may see this come to.
Yes.
And so that means I go into that today.
But if you use quantum entanglement for communication, that actually has built-in security, security built into the communication method itself. So it's going to change everything that we know about computing and also computer security. So getting to know what it is, can be useful. Just knowing what is a quantum computer, and at a very kind of superficial level, what is quantum physics, that can be helpful. Because by the time you actually do have quantum computers, that are deployed, it won't be very foreign to you. You at least understand the concepts. But it's really interesting, because quantum physics itself is not something that clicks with a lot of people, because it's weird. Even Einstein, okay, I was watching this documentary yesterday, and it says, the guy said, well, if you feel confused and overwhelmed by these concepts, it's okay, because Einstein also got confused and overwhelmed by the same concepts. But it is going to happen at some point. Yep.
What are the methods to stop like a router attack?
To stop, okay, so first of all, you want to make sure that your router has the updated firmware. So depending on, older routers are probably more susceptible, because the manufacturer might have stopped updating the firmware already because it's too old. But with newer routers, you want to either have the router to have auto update, okay, or you go in and check the update of the firmware and keep an eye on your security related issues with that particular model. Does that answer the question? Okay. Has anyone gotten hacked, or that you know of?
I remember last year, our last professor, Hermley, said, don't use the same password for multiple sites, and I used to do that. He's like, yeah, that's dumb. The day after he said that, a couple of my accounts got hacked.
Oh.
And so I started using like a form like hash, where I have a master key, a super long master key, stored in one specific spot that kind of like changes up trends.
Okay, you first, and then back to you. Yeah, go ahead.
Well, I don't know if it's maybe an example of my account getting hacked, but I remember it happened at one point with my Netflix account. At one point, I got an alert saying that someone from China or Guatemala had tried to get in.
That's possible. Someone is trying to hack. Yep, go ahead.
Yeah, about a month ago, my Google account said that somebody from like Zimbabwe tried to like access it, and it was like, is that you?
Yep. So aren't you glad that Google at least is paying attention to where the request is coming from, and go like, this is out of the usual pattern?
That's not what we know you as.
Yep.
This is probably more my fault, but I ended up like downloading what turned out to be spyware, and my ISP was using it to bust me for piracy.
Oh. Now I do have one example. This is from someone whom I know. So he was helping to manage the network and also some of the infrastructure for a fairly small company. And one of the employees opened up an email, in a phishing attempt, and actually provided, some, crucial information. Now, this particular employee was not even high ranking in the company, but they were able to use that as a gateway to hack into the system. And then they proceeded to, first they tracked down the backup chain of the company. So they found out that okay, here's the backup server, and that is in return backup over here. So they figure out the entire thing first before they encrypted everything from the furthest end backward to the most accessible link. Yeah, and then they demanded ransom in bitcoins. So for about a week, that company just could not operate because they lost access to their client list, they lost access to the inventory list, they lost access to everything that they needed to run the company. The good thing was this guy had a little stash of backup from about a month ago that the hackers did not get to. So it's either offsite or it's a very obscure place where the hacker did not think of getting to, and he was able to restore everything to about a month ago, which is much better than not being able to restore to anything at all. So it did happen, to in real life.
Happened to my company too. We had a phishing attack and they shut down nationwide booking for like 3 days until they could recover.
Yep. Go ahead.
I saw a news report that said that there's like an increase in like spam calls or something. And I think that they're like getting information from that or using that information to create like a database.
Well, but in this class we're focusing mostly on things that can be cracked technically. So phishing is kind of more of a social engineering kind of hack. So they're hacking people and the way people think, but not so much technically hacking stuff. Someone can hack my right the Fitbit. It can ruin the app on my phone. And then on my phone, if they can get the information on my phone, that can go to many other things that I have access to because we all have a lot of accounts that we maintain on our phone. Okay, healthcare, banking, insurance. Okay, so we have a lot of really valuable data on the phone. So if somebody can hack in through the Bluetooth first into the phone into my watch and then go backwards, yep.
I remember playing Call of Duty, the World of War, and I wanted to do hacks for zombies because I saw it a lot. So the process was someone created a different version of the game and installed mods on zombies and a disk, but the Xbox wouldn't run the disk because it had to be signed. So what you have to do is you have to open up your Xbox, open up the disk tray. So while the game was running, you would have to swap it out with the hack version. So it would think it was the same game, and then you could play.
Well, but in that case, it's not hacking because the way that I did in today's class. And you invited it too.
Right.
It was a hack that you actually wanted. All right. So so there's no new lab for today. I will be over at the lab. If you want to continue with your homework assignment and have questions to ask, I'll be at the lab to answer those questions. And then on Wednesday, we'll talk about the practice exam, and I'll post the exams. There are some online already, but I can post one more from last semester. So I'll see some of you on Wednesday, and the rest I'll see you over at the lab.
Sir, I was not able to make it to the class last week, for I think on Wednesday. So there was a new lab. I just wanted to see if I could get the code for the.
Oh, that's the last one.
Yeah, the very last one.
Struct. Struct. Struct.